Watch this. A developer opens a search box and types a question. Where do we retry failed payments? Behind that box sit 2,000 repositories, 50 million lines of code. A quarter of a second later, the right answer comes back. A function called enqueueChargeRecoveryJob. Now look closely. No retry, no failed. Not one single word from the question appears in the code it found. So how did the computer find it? That's not one trick. That's a hidden pipeline with a dozen moving parts. And by the end of this video, you'll know every stage of it. First, a confession. Every code search box is secretly two different products. Sometimes a developer knows exactly what they want. A feature flag named checkout experience E2. They want every place that exact string appears. Nothing clever, just find the string. But sometimes they only know what the code does. Where do we retry failed payments? And the actual function might be called schedule charge attempt after failure. Not one shared word. The first problem is matching strings. The second is matching meaning. And a system built for only one of them quietly fails at the other. Therefore, modern code search is built in layers, and the foundation layer works like a library. The foundation is a lexical search engine, in our case, OpenSearch. Think of it as a library, obsessed with the index at the back of the book. Instead of reading every book to find the word payment, it pre-builds a giant reverse index. Every word, mapped to the exact list of documents containing it. Searching stops being reading and becomes a lookup. But a library holding a whole company's code needs structure. So, learn 5 words. A cluster is the whole library. A team of machines acting as one. Each machine is a node. An index is one catalog. Ours is called code chensions. Each entry in the catalog is a document, maybe a file, maybe a single function. And the load-bearing word, a shard. A shard is one drawer of the catalog. 10 million documents won't fit in one drawer, so OpenSearch splits the index into shards and spreads them across the nodes. Why bother with drawers? Scale and speed. Split 10 terabytes of index code into 10 shards, and one query can search all 10 drawers at the same time. In theory, 10 times faster. In practice, less. Because someone has to fan the query out, collect 10 piles of answers, merge them, and sort them. More shards buy more parallelism, but cost more coordination. It's a dial, not a free lunch. Then there's the second dial, replicas. Every shard gets a copy living on a different machine. If a node dies at 2 in the morning, the copy keeps answering. That's fault tolerance. But copies aren't just insurance, they're capacity. If one copy of a shard can handle 50 queries a second, a primary plus one replica handles about 100. Add a second replica, 150. Here's the bill. A 5 terabyte index with one replica needs 10 terabytes of disk. With 2, 15. Reliability is storage you pay for in advance. But the smartest sharding decision isn't about size at all. It's about placement. Developers overwhelmingly search inside one repo, payment service, retry payment. If that repo's documents are sprayed evenly across 100 shards, every repo-scoped query still has to ask all 100 drawers. Keep each repo's code physically together in 2 or 3 shards, and the exact same query touches 3 drawers instead of 100. Less fan-out, less merging, less latency. One huge repo might still need 3 drawers to itself, and 1,000 tiny repos can share. The principle is worth tattooing somewhere. Arrange your data the way your users ask questions. So is matching solved. Matching was the easy half. Say someone searches charge customer. The engine finds 5 matches. The function definition, a comment mentioning it, a test that mocks it, a documentation page, a log line, 5 matches, 1 right answer. Deciding which comes first is ranking. And ranking is where a search engine encodes opinions. Opinion 1, where the match happened matters. A hit in a function name might count 10 times. A class name, 8. A file name, 5. A comment, 1. Run the numbers. A result with a modest text score of 2. But, in a function name, scores 20. A result with a juicy score of 5, sitting in a comment, scores 5. The definition wins, exactly as a developer would want. Opinion 2. Alive beats archived. 2 files match. One lives in a repo retired 2 years ago. The other shipped to production last month. Multiply the archived one by 0.2. Its 10 points collapse to 2. Boost the production 1 by 1.5. 10 becomes 15. But handle this opinion with care. A 10-year-old utility function that never needed to change may still be the right answer. Freshness is a signal, never a verdict. Underneath all those hand-tuned boosts sits the granddaddy of ranking formulas, BM25. 3 intuitions, decades of refinement. 1. Repetition saturates. A document mentioning your term once is a clue. 5 times, a stronger clue. But the 50th mention adds almost nothing. The value follows a saturation curve, and that's what stops a bloated file. Chanting payment, payment, payment from beating one focus function. 2. Rare words are gold. In a 10 million document codebase, the word function appears in 6 million documents. It tells you nothing. Charge customer appears in 20. When a query contains both, BM25 bets nearly everything on the rare one, which is precisely why searching one weird identifier works so well. 3. Long documents get no credit for being long. And that triple is exactly where BM25 beats its ancestor TF-IDF, which kept over-rewarding repetition and bulk. And typos? There's a layer for that too. Fuzzy search measures edit distance. How many single character changes turn what you typed into something that exists? Function to function. A few small edits. Close enough, match it. But fuzziness is a loaded weapon on short strings. Loosen auth by a single character, and you've matched path, auto, and math. Pure noise, so real systems stage it. Exact match first, fuzzy only as a fallback, and almost no fuzz on short identifiers. Precision first, forgiveness second. Now for a quiet decision that shapes everything downstream. The schema. Every field in the index gets declared as one of 2 types. A text field is chopped into tokens. Retries a failed payment attempt becomes retries, failed payment attempt. Perfect for full text search. A keyword field is stored whole and untouched. Checkout. Xbrand's A2 stays one exact string. Perfect for filters and exact lookups. Declare the flag name as text and it shatters into checkout. Experiment V2. Exact flag search dies. Declare code content as keyword and full text search inside code dies. So mature systems simply store the same information both ways. Schema design sounds like a back-end detail. It's product design. Every field type is a promise about what users will be able to do, which brings us back to the mystery from the beginning. NQ charge recovery job shares 0 words with where do we retry failed payments. No amount of lexical cleverness will find it. Enter embeddings. An embedding model reads a piece of text or code and assigns it a point on a giant map of meaning, a vector of hundreds of numbers. The numbers mean nothing to humans. The distances mean everything. Retry failed payment and attempt charge again after a transaction failure land almost on top of each other, because the model has read enough of the world to know they're the same idea in different clothes. Index every code chunk as a point on that map. Store the points in a vector database. And search becomes geometry. Embed the query, find the nearest neighbors. The function with 0 matching words is simply the closest point on the map. That's the trick from the opening. That's how the magic happened. But semantic search has a brutal dependency. What exactly do you embed? Embed a whole 2000-line billing file, and you get one blurry point that means billing, sort of. Search refund logic, and the system shrugs. It's somewhere in these 2000 lines. Embed 3 lines, and the point means nothing at all. If attempts less than max, NQ the job. Is that payments, emails, a video game? The chunk has to carry meaning on its own. A function, a class, a test, large enough to preserve meaning, small enough to stay focused. So how do you cut code at its joints instead of every 100 lines? A parser called tree sitter. It reads source the way a compiler's front end does. This is a class, this is a method, this is a comment, and hands the indexer clean, meaningful chunks. 2 bonuses. It labels where every match lives. Class name versus string literal, which feeds exactly the field boosting we built earlier. And it's incremental. Edit 1 function in a huge file, and it reparses just that region, the only way an index stays fresh at thousands of commits a day. So now we hold 2 engines, lexical for exact strings, semantic for meaning. The best systems refuse to choose. They run both and merge the candidates. Here's the whole architecture in one breath. Retrieval is broad and cheap. Ranking is narrow and smart. Stage 1 skims 100 million chunks and keeps maybe 200 plausible candidates. Stage 2 is a cross-encoder, a model that actually reads the query and each candidate together, like a human reviewer, and scores the pair. It's the most accurate judge we have, and the most expensive. At 10 milliseconds per candidate, scoring 200 costs 2 full seconds. So you only show it the top 50. And above it all, mature systems learn to rank. Every click, every opened file, every ignored result becomes training data, blending BM25, vector distance, exact symbol hits, freshness, and popularity into one final order. Does this hold up at company scale? Let's do the napkin math real engineers do. 1 million daily users, 5 searches each. 5 million searches across 86,400 seconds. About 58 queries per second, on average. But nobody builds for average. Peaks run 10x. Call it 580. Each query fans out to 20 shards. 11,600 shard-level operations per second. At 1,000 per node, that's 12 nodes. And you provision 24, because running at the red line is how outages happen. Latency obeys the same parallel logic. 10 shards at 80 milliseconds answer in 80. You wait for the slowest drawer, plus 20 to merge. 100 milliseconds, not 800. And the full hybrid pipeline. Embedding 20 milliseconds. Vector search 50. Lexical search running alongside 80. Merge 10. Re-rank 150. In sequence, that's 310. Overlapped 240. Every millisecond placed on purpose. One final layer, geography. Data residency laws can require European code to stay physically in Europe. So you run a full stack per region. Indexers, clusters, vector databases, dashboards, and every schema change, every ranking tweak, rolls out 3 times and gets tested 3 times. That's why teams resist multiple clusters until law or latency forces them, which reveals the real shape of search expertise. It's all dials. More shards, more parallelism, more coordination, more replicas, more capacity, more disk, more fuzz, more forgiveness, more noise, bigger chunks, more context, less precision, more re-ranking, better order, more latency. An expert isn't someone who knows the magic setting. It's someone who knows what every dial costs. So close the loop. 1/4 of a second, remember? In those 250 milliseconds, the query was tokenized and embedded. 10 drawers searched in parallel. A vector database measured distances on a map of meaning. 200 candidates merged, boosted, demoted. 50 of them read, word by word, by a model trained on 1 million clicks. And the function with 0 matching words came back first. It feels like magic. It's the exact opposite of magic. A dozen unglamorous decisions, all pointed at one question. What was the developer actually asking? Great search isn't one clever algorithm. It's an entire system agreeing on what relevant means.